All right. As a full-time maker, YouTuber, and scientist, Jay Bowles has a passion for high-voltage physics. In this talk, Jay will utilize a combination of on-stage demonstrations and pre-recorded videos to be played on the slides, ultimately inspiring as many people to build, create, and engineer as possible. Please welcome to the Hackaday Supercon stage, Jay Bowles.
Thank you. Thank you, everybody. Now, a quick note before I begin. I've spent the past 2 days chatting with a bunch of you guys, and I just want to level the playing field here. I've been completely humbled by all the people that I have met up until the very last second of coming up here on stage. This is my first conference I've ever been to, and I've been told it's the best one to come to, and it sounds like a really great start to me. I've been really impressed by everybody here. Now, when it comes to me and content production for YouTube and then Hackaday, I've been in communication with Hackaday for a couple of years. And the funny thing is, I'm in communication a few months ago, and they say, hey, we're doing this Supercon coming up. Have you considered wanting to do a speech at all? And I said, oh, well, I guess I could give that a try. And they said, yeah, we can't guarantee you'd be accepted for a speech, but give it a try. So I submitted it, and I was like, oh, it's not going to be accepted. No big deal. I won't have to make a speech. And then I get an email like a week or two later saying, congratulations, you have a 45-minute slot. It's like, all right. Now I'm really, really passionate about this little sliver of physics, and it's my goal to try and spread that passion. So my 45 minutes turned into more like 450 minutes. So I hope you guys are okay with that. But to get started, and I think I can probably expect to see a couple of hands be raised. Can I see a show of hands who in the audience, either professionally or personally, has spent some time in the thrones of high voltage electronics? Oh, dude, that's more than I thought. That's awesome. Did you guys see the demonstration yesterday with the neon sign transformer? Yeah, that was pretty cool. Well, if you zoom it out, and I'm going to start very basic, and then get more narrow into why I'm very passionate about this stuff. And they mentioned there's a lot of visuals. There's actually a lot of video content here. On the most basic, zoomed out perspective of what electricity truly is, right, is the ability to do work carried by a wire, right? The ability to do work carried by a wire, or the earth and the air in terms of wireless power transmission. It's really quite a fascinating, concept altogether. And but most of the electricity we all know is the electricity we see in our daily life, which is the 120, 110 volts coming out of our walls, the 12-volt car battery that we're used to, or, well, now it's 450 lithium-powered batteries, but, or the 5-volt USB, or the 1 to 12 volts that you see in the logic circuitry for a lot of computers. And that's electricity we're all used to seeing, myself and, before you're initiated, so to speak. That's what you're used to. And that's all phenomenal. And that's why I say I've been humbled while being here, because there's a lot of programming here, a lot of soldering going out back, and it's been a humbling experience. However, my tastes lie on a little bit different side of the coin. And unless you work in the power distribution and generation industry, so nuclear, coal, wind, any kind of power generation you think of, unless you work in that industry, you're not going to see the other side of the coin, really. And as I've alluded to, the other side of the coin, the side of the coin that inspires me and motivates me and honest to God wakes me up in the middle of the night at 2 a.m., I don't know, it's something. I'll wake up at 2 a.m. and just suddenly have an idea and be like, I got to go experiment on this, I got to go try this. The other side of the coin that just captivates me is the high voltage side. And there's a lot of reasons for that, but I'll get into those throughout the talk. And the talk's going to consist of me trying to make a compelling argument of why I think this is the most fascinating field of physics, and why I think and hope that all of us walk away feeling a little bit curious and a little bit inspired. So I'd like to welcome you all to a little slice of paradise that I like to call the Plasmaverse. Is it going to play? some of those clips were pretty fast, and that was the plan. I'll have a lot longer clips throughout the speech and broken down sections of some of the stuff you saw. The very end, actually, that slow motion spark you saw is the solid state coil I brought here, solid state Tesla coil. I don't have a phantom camera on me, unfortunately, to do that slow motion footage again. But yeah, thank you everybody for being here. I see a lot of familiar faces and a lot of people I've talked to throughout the weekend. So like really, really grateful that you're here. My full name is Jason Bowles. I professionally go by Jay. And I'm the host, the producer, the one-man show behind a YouTube series called Plasma Channel. And long story short, it's just my attempt to share a passion of physics and high voltage and this entirely other side of the coin. That is plasma physics. Now, in the beginning, I was also known for doing slightly more dangerous things, like trying to prove that $10 Amazon tasers don't bring you down. Here's the science. You know, beginning YouTube and all. I made my point though. Don't buy $10 stun guns off Amazon. They don't stop. They hurt really bad, but that's it. Yeah, I didn't show the marks on that video. But you know, as I've mentioned, like this is my passion. It's like a slight obsession. It's a passion. It's something that wakes me up in the middle of the night. And what I mean by that is it's the most beautiful field of physics, I think, analogy-wise and visually as well. This is what I'm passionate about, plasma. It's in the name Plasma Channel, and it's what I see on a daily basis. And it's really, really hard to make a point to say this is stuff that you'll regularly see in your daily life. Mostly because, you know, we're not surrounded usually by really high thresholds of voltage. But when you get to that point, there's some pretty remarkable things that are possible. What's really cool, upper right corner, that's Kirlian photography. I'm sure, can I see a show of hands who's heard of Kirlian photography? Yeah, it's actually like, it's really sick. It's cool. Now let's break it down a little bit. Because it is my goal that you walk away curious. I want you curious. Because what made me curious in the beginning was way back in high school. Maybe some of your high schools were the same, I don't know. There was a day where all the clubs would have a table showing, you know, what you can do in the club, and the electronics club had a Tesla coil, right? And all it took was that one interaction to completely radically change my life. They told me I wouldn't get hurt. I actually got burned by it. But it's like all it takes is just a little something to make you raise your eyebrow. So let's dig into this field, high voltage physics, and you know what exactly it means. So breaking that down, high voltage that I work with typically define that as over 360 volts. And physics, as we all know, is a field of study chiefly concerned with using overly complicated and overly long equations to describe how a ball rolls downhill, even though we can already see it rolls downhill. Totally true, but physics is the master of all sciences. I absolutely am passionate about it, and it is a branch of science chiefly concerned with studying the interactions of matter and the structures of matter and how it works in the universe. Putting those two together, as you might guess, the interactions of matter at extremely high voltages, which hopefully you'll see at the end of this talk. Oh, it's like the closest thing to magic that I've personally ever seen. It's phenomenal. Now, I mentioned 360 volts. Quick note about that. That is not universally agreed upon in terms of what you call high voltage. Last I checked, OSHA defines high voltage as anything over 50 volts. Come on, man. And there's some European unions that define it as between 600 and 1,000 volts. I forget what the American Society of Electrical Engineers refers to it as, but I've always operated underneath, and as well as a lot of high voltage enthusiasts and makers like myself, we define high voltage as the moment you can have continuous ionization jumping a gap in a circuit. So let's say you have a certain voltage, it's usually around 360 volts. You take scissors, you cut the wire. You put the wire back together very, very close, say 1/10 of a millimeter gap, something extremely small, and the electricity does not care. It'll ionize that gap. The voltage is just high enough that that's the moment it becomes a little bit more unstoppable. So around 360 volts. However, as I've alluded to, that is not where the magic happens. Vegeta here knows a little bit more about that. You get into the thousands or tens of thousands of volts, and that is where you can do some really phenomenal things. The field of physics really, really touches on, quite frankly, things that I'll show you that absolutely we would have burned at the stake back in Salem for. It looks like witchcraft. So most of the lecture will focus on voltages. The lowest voltage would be about 3,000 volts. The highest voltage is a few 100,000 volts DC. And that's really where the magic happens. Now to get to these voltages, you know, when you first start out, it's like, oh, how the heck do you do that? That seems like something only like a power company or a power line can do. It's actually quite amazing. Over the past 150 years, people have been very brilliant with creative ways to produce insanely high voltages and ways that are kind of cheap. And those include Van der Graaf generators, which for those who aren't familiar and those watching, that's the thing you put your hand on and your hair stands up. Tesla coils, which I brought here. You got Marx generators, which are impulse generators. You've got voltage multipliers. I was going to bring one, but TSA was not the biggest fan of that. I already had to explain this giant 6-inch metal spike I was hand carrying on the plane. But yeah, there's a plethora. There's Wimshurst machines, there's ignition coil drivers. There's a whole field, a hobbyist field of ways to generate really high voltages that you can build in your kitchen in 2 or 3 hours. And so it's my passion, not just this field of physics, it's also my passion to build these devices. I also like using acrylic a lot. Some of the people who are here have seen my videos know that I'm kind of obsessed with acrylic. But it's also part of my passion to go ahead and use those to create videos and make educational points. Yes. So an example of that, I think this was last Thanksgiving, and I'm standing on a plastic Tupperware container that somehow supported my weight, and I'm electrically isolated from ground. When you do a demonstration like this, the Van der Graaf is going to charge you up to a sufficiently high voltage. Some of you might have done this before. The amazing thing about something like this, it's a great teaching tool. You can literally point at an object or a person, and if they're close enough and if you're charged to a high enough voltage and enough power is going through you, you can point at something and you'll charge that object up. So I told my nephew and niece, I was like, hey, Papa's getting charged up, go touch him. Go touch him. And they learned that if they touch Papa, he gets shocked. And he's like, ow, ow. So they just go poke my father, and he gets shocked to death. And that's a picture of them just losing their mind, shocking him, because I'm charging him up against his will. Yeah, so I try to do a little bit of outreach, and I try and share that passion really any way I can. And that is, that's the purpose behind this. Back to the name, though, of like high voltage physics. High voltage is kind of a sensationalized term. I've seen high voltage energy drinks when I lived in Austin. I saw High Voltage Coffee Co. It's a very sensationalized term. But if you ask me, the field of high voltage physics, which is closely tied to plasma physics, if you ask me, some of the things it touches on and allows for are pretty sensational. So there's a little bit more you saw of the Curlian photography. That's one of my favorites. It's phenomenal. But the case I'm trying to make is there's an entirely other world that is kind of around us at all times, but unless you've kind of been initiated to it, you don't really necessarily see it. So let's break down a few of the examples, well actually several of the examples, and depending on time I might skip one or two of them, and talk about those in more depth, go figure, see a little bit more video, and then talk about the why. Like, why do I find it fascinating, and why I think and hope that you will as well. So starting out, let's talk about the thing that totally would have gotten us burned at the stake in Salem, and that would be electrostatic firebending. A little more video coming up. And this is a really old video of mine. I used to use a lot of hair wax. Yeah, and so that was from like 4 or 5 years ago. I was just starting out. I absolutely burned myself really bad while making that video. Go figure that attracting fire to your body would potentially burn you. But yeah, so not CGI. The physics and science behind it is extremely, extremely simple. You know, you'll see here shortly that it's more or less a very simple electrostatic science. Now, breaking down how that works, plasma is the fourth state of matter, and that consists of a superheated ionized gas. Or you could argue it's kind of a cloud of charged ions. That being said, plasma is easily influenced by positive and negative external charges. And this is a well-known fact. Now, fire, on the other hand, is arguably, and up for debate, considered a partial plasma. And there's several reasons for that, but it does have charged ions in it, partially from the combustion process, but then also it kind of does fringe on the edge of being able to ionize the gas. But that's also why it's up for debate. But I err on the side of calling it a partial plasma. So that being said, it will interact with external positive and negative electric charges, just like plasma. But what's the deal here? There's your charges right there. But when you're using your hand or using any other object, right, very simple concept, you're not an electric charge, you're a hand. So how do you turn yourself into the equivalent of a point charge? Well, let's take little Susie here, and you go ahead and take 50,000 volts DC, and you zap her body with that. And apparently she's missing her arms. Well, here's the overcoming adversity in that one. But when you do so, you effectively become, a point charge, a source of a static charge, whether it's negative charge or positive, depends on your source, right? And that is basically all it takes to be able to have the power to influence any type of flame. Now, I have found that the flame source does make a difference with how easily it is attracted to an object or to your hand, whatever you're choosing to use to attract. Now, a combustion style using wood does have the strongest effect, which also makes the argument that those ions are partially from the combustion process. But there is a mild difference in effect depending on propane, methane, isopropyl alcohol. Isopropyl works actually really well, but yeah, you burn yourself a lot more easily. Let's talk about the point that I'm trying to make, which is shoving 50,000 volts into a human body. I'm talking to a demographic that probably already understands this very well. For people that are watching, there's multiple elements that come together to make electricity what it is. It's not just voltage, it's not just current. They all come together to make a medley, this soup. And it's, voltage is important, current is important, the time constant, so how long your body experiences the power flowing through your body is important. The frequency at which the electricity interacts with your body is extremely important. Are you isolated from ground, or is the power flowing through through you to ground? These all come into play, but the point is that voltage explicitly alone does not necessarily dictate that it's going to be extremely dangerous for you. You have to take into account the other things. So I'm not advocating you go shock yourself with 50,000 volts without being safe. But how would you go about doing that? Well, I alluded to it earlier with the devices that you build, but my favorite, because the safety is through the roof on this one, would be a Van de Graaff generator. You will rarely find a Van de Graaff that produces enough current, even with a discharge from the dome, to like really do significant damage to your body. They pump out microamps. Now another option is voltage multipliers. That's what I was going to bring. That TSA was not a fan of. But yet they let this through. I don't know. And so I like to build these. It's, like I said, part of the passion. Recently I've been encapsulating them in epoxy. They last longer. It boosts the power a little bit. And you can design voltage multipliers. They're essentially a circuit. They're one of the most basic circuits. All there is to a voltage multiplier is a diode and a capacitor, and then you repeat that pattern back and forth, literally like a physical ladder that you climb on, right? So they're easy to design and easy to predict and calculate the current output. Therefore, you can design one safely and then attach your body to it and start doing these semi-dangerous experiments. Now, I have found that at about 20 kilovolts DC of steady charge on your body is where you start to get the effect of firebending, or like I said, if you choose not to use your body, some other object. It seems to be about 20 kilovolts DC is where the effect starts to be very noticeable. And then at 50 kilovolts is where you see the effect that the video, and then I think there's a still frame coming up, is where you'll see like the full-blown effect. But here's why I argue this is more than a party trick. This is really cool. I haven't had the time to dig into this yet. But so 20 seems to really start to be prominent. 50 is where it's in full strength. And what's really, really cool is I found above 50 kilovolts, fire struggles to burn oxygen in a static electric field that strong. And I've even gotten some footage of it suppresses and extinguishes the fire. And there's a lot of reasons for that. Everything from ionic wind to static fields, and but it makes me wonder, can we not dig into this a little bit more? It's technically such a basic idea, a static charge, and that is it. But that's the why behind why I think this is really important, besides just doing a party trick with controlling fire, is can we potentially suppress it in the future? That would be something really cool to dig into. Cool. But yeah, so this was actually a still frame not taken by me, but I think that's the exact moment when I really badly burned my hand, because you don't just have fire flowing through you. When it actually touches you, now you have a little bit of current as well, and it's a double whammy that your skin really loves. Next up, let's talk about ionic wind, I believe. Ionic thruster, there we go. Oh! So fans and blades are not the only way to accelerate air. That was from a very recent video of mine that was my attempt at interpreting the answer to a question that I posed to myself, which was, if a turbine is the evolution of a propeller, what is the evolution of like a simple ionic thrust setup? How do you optimize that setup? And I wanted to make like a modular design that you could bolt onto something, or almost like a turbine, but it's like ionic thrust and power. And as you'd guess, with an ionic thruster, it uses a process called ionic wind, and that is not the ionic wind that comes from a sun. It's generated through a different process, but I thought it would be important to note that. And how the ionic wind works, again, is actually like very simple. Science, many of you in the audience might be familiar with this. Quite brilliant, quite simple. Take, say, 40 kilovolts DC. It has to be DC. I've seen experiments do it with AC, but it works 110% better with DC. Apply that to 2 electrodes and space them out a couple inches. And what happens is, apply that. What happens is the positive electrode rips electrons off the surrounding air molecules. They're repelled away and they go towards ground, which is on the right, and they bump into other air molecules along the way, and they create ionic wind, and that's called electrohydrodynamic thrust. It's a mouthful of a word, but it is one hell of a really cool process. And that, as you might guess, shows one of the simplest setups you can possibly do for ionic wind. That is not a complex process. That was basically a wire and then a grounded pipe. You can set that up in, as long as you have the power source, it takes 5 seconds. If you want to get any real kind of output, you need to compress more of those electrodes, both positive and negative, into the smallest space possible. And that is kind of what I attempted to do with my thruster, which this is the thruster that I built. This is when you turn out the lights. This is why I love high voltage physics. Like, this is what keeps me up at night. I think it's so beautiful. Now the electrodes, breaking it down, these are repeating sections. So where you see the green one, that's another section. The positive electrode is a snaking, I think, 6 or 7 meters of wire. And the ground electrodes are these brass tubes that are connected in series as well, right in front. You can see them right in front of the green. And I found this did manage to get more of a sufficient airflow going, about, I think, 2.3 meters a second. And that is a 6-inch diameter, internal diameter of that thruster that it's moving air through. Lot of room for improvement on this prototype. Lots of room. I have a friend over in Portugal who completely destroyed me with his thruster. But I did find, at least with my iteration, that if you want to make an ionic thruster and you want to make it modular, it's also super beneficial to make it like a series thruster, a bit like a LINAC. So each section on the thruster is a repeating section that's very loosely identical, and they feed into each other and accelerate the air faster and faster, like I said, just like a LINAC. Next up, that is, well, it's about as witchcraftery and wizardry and Hogwartsy as the firebending would be that car that just drove by. Is electrostatic levitation. So, out of all the experiments you can do in your kitchen or your garage or anywhere, this is one of the, when you do it, it's one of the most fascinating feelings. Like if you use your hand, you actually feel it tugging on your skin in a way that you've never really felt before. It's quite fascinating. But the best part about this, when it comes to levitation, electrostatic levitation, as long as you have the power source, it's one of the quickest experiments and demonstrations to set up, which is amazing. All you really need, again, once you have the power source, is 2 metal plates. They need to be perfectly flat, perfectly parallel, and you space them 5 to 7 inches apart. If you use a lower voltage source, you can make that distance a little bit shorter. Super critical, they need to be electrically isolated from one another. I'm, again, obsessed with acrylic, so I used acrylic standoffs in that case. And that is about it. The ground, the bottom plate is going to be electrically grounded, and the top plate will have a very strong negative DC voltage applied, anywhere from 30 to 50 kilovolts DC. And then what's also really important is the electrostatic levitation is not perfect. You can only levitate certain shapes and certain kind of mass limits, and it's kind of at around 0.5 gram to really 1 gram at most. The shape of the object you want to levitate is at this time very important as well, right? So you'll notice the top is curved, the lower corners are sharp. There's a specific reason for that, and that's what helps make this be a self-regulating levitation. It gets more complex, which I'll talk about. Self-regulating and also allows the whole process to work is actually the specific shape of what you're levitating. It's actually pretty cool. So, you've got your power source. You've taken all of 23 seconds to set it up, and you turn on the power. Well, what exactly happens? Well, first, if you start out by putting the piece of foil, say, on the ground plate, well, you're sitting on the ground plate. That's foil. Foil's conductive. So you go ahead and turn on the power, and the plate is about 5 inches above, and what it does is skip a slide. That's what it does. What it does is it repels electrons down to the ground plate, and it leaves that foil slightly positively charged. Well, strong negative charge up top, positively charged piece of foil. It, go figure, creates a charge imbalance in the system, and it flies up to the top. But you'll notice, if positive is attracted to negative, why doesn't it just go to the very top? Let's play that again. Oh, nope, let's play that again. Yeah. It stops just short of the top. So with like really simple base level understanding of attractive forces and repulsive forces of positive and negative, it's like, okay, there's something else going on here. And that is where the science gets a little bit more deep. It self-regulates, like I said, using that shape. So the foil is attracted to the upper plate, right? But it kind of digs its own grave. As it gets closer to the top plate, that top plate is strongly negatively charged. And keep in mind, any sufficiently charged surface that has a strong static charge on it, that charge is always looking for a way down to ground. It's always looking for an opportunity out. And when it comes to a strong electric field, having any sharp points near that strong electric field, such as an inch beneath your plate, it acts like a lightning rod. It allows charge to leak away from the plate and actually attach themselves and go into the foil. And you might ask yourself, well, power is being applied to the top plate, so why does it matter? Well, before you had power that was maxed out with the charge, but now you have an open garden hose of charge also leaving because of the sharp point of the foil in proximity to the static charge. So what you have is vertical regulation via charge loss. And like I said, it digs its own grave. The closer it gets, the more charge it leaks away, and then there's not as much attraction to the top plate. Now something else happens that is also involved. You have the negative charges up top, which will repel the additional electrons in the foil down to the corners. When that happens, I don't know if you guys can see this. Can you guys see those little purple trails? Okay. So it regulates itself, like it opens up a garden hose and reduces charge when it gets up top, but simultaneously it uses that charge it stole away to funnel the electrons into the sharp corners, and it creates ionic thrust out of the corners. So it digs its own grave, but then also uses that to thrust itself upward. Little confusing. So it falls, it climbs, it falls. It's kind of doing both at the same time, and welcome to the crazy world of quasi-stable levitation. This is a type of levitation that requires a constant input of power to make it work, and it's dictated by a thing called Earnshaw's theorem. In complete layman terms, Earnshaw's theorem basically, it's quite brilliant, dictates that, say a point charge, like this ball, if you put it perfectly centered in a symmetrically charged field, and you put it perfectly centered, it is impossible for that charge to not go towards its resolution, to not go towards one of the sides, to one of the opposing charges. You can center it down to an atom. It's still going to go one way or the other. It requires energy to keep it in the center, not unlike a ball rolling downhill. Or in the case of the levitation, the power you're constantly putting into it is to prevent it from sticking to the top or falling down. And so it's called quasi-stable levitation because it's not truly stable, but the power you continuously pump into it allows for that stability while the power is turned on. It's really cool. Now, it's a semi-new idea. It's been around for several decades. And NASA in particular did some notable things back in 1993. They made a dedicated electrostatic levitator, but it was a bit different from this type of foil levitator. Theirs requires a vacuum. It was not self-regulating in terms of just the shape of the object, but it needed electronic feedback. And also, if I remember right, the ball, yeah, they were able to levitate a 2-millimeter ball bearing. This was kind of the advent. The field has improved since then, but that's why I like the foil idea better because it self-regulates. It's phenomenal, and you can do more than a 2-millimeter wide metal alloy ball. Implications for this: I would love to see additional work being poured into this to see, well, can we levitate a 5-gram object, a 10-gram object, a 20-gram object? Are there things we're not looking at? Are there things that we have yet to discover? And I think that has implications for everything from, say, we know about maglev trains. Can we start experimenting with bigger objects, with transportation, with helping out carrying of loads? Next up, Another thing that is really, really fascinating about high voltage physics is it's around us all the time. I showed a quick clip of it. Because of the atmosphere, because of the ground, there's atmospheric energy. So I warned Hackaday that their live feed might have a lot of conspiracy theorists now flooding their comment section. Yes, it is absolutely true. You can siphon energy directly out of the sky. You don't need clouds. It doesn't need to be a stormy day. There are conditions that make it impossible to do so, but there are days that make it much better. It's crazy. I heard about it, and I thought I was like, that's impossible. No. But then you actually read into it, and I've spoken to a lot of radio operators in the room. Can I see a show of hands who here is an amateur radio operator? Yeah, so you guys know exactly what I'm talking about already. There exists a voltage gradient between the Earth and the atmosphere at all times. It's amazing. I've read a bunch of sources on it. They don't seem to fully agree, but the most reliable source I found, it's about 120 volts per meter from ground level. Ground, of course, being 0, and as you go further up into the atmosphere, that voltage gradient gets more and more significant. Again, it's a gradient basically like a charged plate situation with parallel plates. You've got the atmosphere and you've got the Earth. So that's what's referred to as the voltage gradient. And it looks a little bit like this. Not physically, it doesn't physically exist up there, but that's the best representation you can kind of have of it. And that voltage gradient, you might be thinking, okay, if it's 120 volts per meter, and let's say I'm 2 meters tall, well, that's almost 250 volts from head to foot. Why am I not feeling it? Bunch of reasons for that, but one of them also being that if you're also attached to ground, you're also loosely grounded. So your head is also at 0 volts. So you don't cut through that voltage gradient and then experience a difference in potential between head and foot. This gets even more extreme. You can have tall objects, buildings, radio towers. Though I've spoken to several of you, it's more complex with the radio tower situation. You end up bending the voltage gradients. You don't really cut through them. And this is really important. This relates to how you extract energy out of the atmosphere in the first place using a drone. So here is how you hack the voltage gradient. Conceptually, when you connect 2 points with a difference in voltage potential, you're going to be having a flow in current. Now, ground will be your 0 volts. And increased height will mean increased voltage. And again, increased height through the positively charged atmosphere. Now, how you go ahead and hack this gradient, which I've kind of hinted at, is you can use a balloon or a drone. I used a drone. I like being able to control it a little bit more. And you take a grounded wire and you drag that up into the atmosphere. Must be grounded on one end. And you go up 50, 100 meters, as high as you're legally able to go. Right, which is 400 feet, I believe, for amateur drone operators. And it's not a big deal. You can't really do much if you took your drone up 3 meters. You can probably measure that voltage potential, but you can't do anything with that. When you get to, like I said, 50, 100 meters, that voltage potential is significant compared to ground. So 100 times 120 volts per meter, we're talking 12,000 volt difference between ground to sky. Keep in mind, anything connected to ground is at ground potential. So now you have the Earth up at 100 meters on a thin, sharp wire surrounded by very, very high tension and very compact electric field gradients. My friend Mehdi, I'm sure a lot of you guys are familiar with Electroboom. He did a good job of kind of drawing that out, similar to the picture I showed earlier, which is you don't end up cutting through the voltage gradients. You end up compressing them around the point. This is very important because related to the electrostatic levitator, those sharp corners in the foil, sharp points naturally will have stronger electric field gradients around them. Combine that with the fact that now you've also forced additional compaction of those gradients around the wire because you've gone up in height, and now you have extremely, extremely strong electric fields around the edge of the wire, which causes ionization of the wire and a transfer of electrons being sucked out of the Earth and then spat into the air. So And you can just drag a wire up into the sky. You won't get much measurable energy from it, but it all boils down to manipulating the fact that there is a voltage gradient between cloud and earth, and the voltage harvested will be dictated by the strength of your ground connection, the height you are above the ground that you're sampling. You can either be in a valley or in a mountaintop, the difference from the height at which the ground wire is attached. And another thing I didn't include is also, do you have the wire insulated or bare? The first test I did, I used a completely uninsulated wire, and go figure, I didn't develop a tremendous amount of voltage because it just leaked away, so to speak. So that's voltage, is what it's dictated by. Current, on the other hand, and this is a picture, as you guessed, from the drone. I wanted to bring this, I forgot to bring this. Before I talk about the current, that's the electrode. It's about 1 meter underneath of the drone, and then the wire is electrically connected to that electrode. The point I'm about to make and why the electrode looks like this, at least I found it worked for my experiments, current is determined partly by the number of sharp ionization points you have to exchange electrons from earth to ground. So the more sharp points you have, the more electron transfer there's going to be, more charge transfer, and then more current going through the wire. So that's why that ended up being the shape that worked best for me. Now, I mentioned humidity is not the best thing. I did a test. I was really excited. I think it was the first time I went out there to do the experiment, and I didn't take into account that it was ungodly humid. It had just rained, and then it was super hot the next day in Seattle. Rare that we see the sun, but we do. And I took it up, got all the camera equipment running. I was really excited to do this physics demonstration. It didn't work one bit. Like nothing. I could have licked it. Nothing. There was probably like 3 volts on the wire. There was nothing. And I maxed it out. I went up to as high as I legally could go. So I went back home and I thought, what's going on? And then I realized, okay, my hair looked poofy. I basically feel like I just come back from Hawaii or Florida, and I was sticky. It's like, oh my God. Humidity absolutely wrecks output with this form of energy harvesting out of the atmosphere. You cannot do it in a humid situation, at least not that I know the method of. I'm sure there's some other way. Apparently humidity reduces output really bad. I put that twice. And the energy you draw is actually quite low using this method. Using a small drone, you're going to pull really at most a watt, less than a watt of power using that. But there's something I want to make a point about, which is, sure, it might be a watt or less than a watt of power. It's the concept that I think is really, really cool. And I have a video with a bit of a story attached to it. Can you turn up the audio a little bit for the next clip? So I was getting ready to set up for a little shot, and essentially I could hear static coming off the wire near me. And so I was like, oh, I'll go ahead and test this. Can I shock myself with it? And that's my go-to. There's something wrong with me. And let's see, you can hear the static as I bring myself near the wire. That wire is on a drone attached about 100 meters up. And I'll play that again just so you like hear the static. It's the coolest thing ever. Sorry. Welcome to my life. Some of that static charge, admittedly, probably is also accumulated through wind abrasion. If you've got 100 meters of wire and wind slash, you've got some abrasion going on, but a lot of that is from the voltage gradient going on. Now, I filmed that little clip after I accidentally shocked myself. So I'm trying to set up this like corona motor to spin, and I'll talk about what a corona motor is in a second. And I didn't realize the drone had sagged down a couple of meters in the sky, whatever reason. So the wire had sagged down right next to my head. I kept hearing like this staticky sound, and I was like, that's so weird. So I instinctually looked to see what it was, and it zaps me right on the eyebrow. And me being as not smart as I am, I was like, oh, that was so cool. And so then that's when I filmed that little clip, and I was like, let's see if you can shock your hand with it. So it may not be a lot of power with a small demo like this, but it's about the concept. It's really cool. I mentioned a corona motor. This is an example of one that I've built. It is like any motor, it has a rotor, but it is what you'd consider a brushless motor that uses electrostatic It turns high voltage DC is what turns it. And you can use extremely low wattages. We're talking like less than a watt of power to make these things turn because they rely on a ground connection and then a high voltage DC, aka a static charge on the other input of the wire to turn. Is that a video? Yes, that's a video. They don't turn very fast. The torque is quite miserable. But there are some people on, there are some creators and makers who have made some really strong Corona motors, and they can get pretty impressive. But that's not something I've really dug into very much. So I said we'd probably see a flood of conspiracy theorists in the comments section for Hackaday. Sorry, Hackaday. The wide-scale use for this. The first thing I thought about is, well, what about the wide-scale use? Why don't we have a bunch of balloons or drones and just like have football fields of collecting terminals up there, collecting this atmospheric charge, which, God forbid, who knows what the trickle effect of that is with altering the atmospheric charge in the area. As cool as it is, it has issues. So the energy density, so to speak, of the land that you're using and the energy you're pulling out is extremely low. It has been attempted in the past. This is one such proposed power station for using atmospheric energy. I believe, 1928, I believe so. So a proposed aerial station, and a part of it was built on a smaller scale. I believe it was one balloon. Out of an entire multiple football fields worth of size, they were able to consistently, regardless of rain or sun, pull several kilowatts. That'll power 1 to 2 hair dryers. So you're going to use an entire football field of land to power 1 or 2 hair dryers. It just, at least in the past, it wasn't fully economically feasible. You can't really necessarily get enough charge density and enough current flowing to really make this feasible for an investor or a builder to get a good return on their ROI. Or even if it's government funded, it's just, you're not going to get a huge flow of energy through this. If there have been any developments in that and it's changed, I would love to hear about them because it's so like steampunky and sci-fi feeling. So yeah, it has been looked at in the past. The reason why we don't do it is because it's just not really worth the money investment. There are other methods to produce far more electricity that we use today. Really, really, really cool idea though, is extracting energy out of the atmosphere. Another more personal use of plasma physics, high voltage. This one, let's talk a little bit about medical. I realized, I don't know if that little plasma flame was visible the entire time. You guys were able to see that? Okay, cool. So, yeah, that was cold plasma. I didn't think it used to be real. I'd heard about it. Yes, it is real. Now, cold plasma has kind of made a name for itself because it has some rather unique qualities. And I'll contrast it with normal plasma, so to speak, shortly. So, in general, cold plasma, as the pictures show, it's going to be touchable. It sterilizes wounds and surfaces without damaging. Extremely low energy usage. It's silent. You can easily make it using limited tools as long as you have the power source, and generally safe to handle. Now this contrasts completely to normal plasma that most of us are used to, hearing about and seeing. That's a still frame of my skin being vaporized by that coil. Doesn't always happen, but sometimes you do. So that's a contrasting issue with cold plasma versus hot. You can't use hot plasma. 5 minutes, thank you. I'm going to speed through this a little bit. I was going to talk about Tesla coils, but I'll go ahead and actually show that instead of go into a big section about them. Now, what's really, really cool, so I mentioned it sterilizes, it kills cold plasma if designed properly. It'll sterilize the surface from bacteria, viruses, prions, fungi, everything you can imagine. And there are a couple small drawbacks, but there's been some research done into using it for medical purposes of sterilizing wounds. Now, to create cold plasma, really rather simple process. So step one, you need your power source. 3 to 5 kilovolts AC at extremely high frequency. You'll want a hot point power source with one side essentially grounded or with a counterpoise, preferably extremely high frequency. We're talking well over 10 kilohertz is where you'll get the best results. Creation step 2, you're going to want to go ahead and shroud that electrode you've provided power to in some kind of insulating tube. So plastic or glass or silicone. But it's key that it's not a tight fit over the electrode. You want to be able to have gas flowing past the electrode. It's also beneficial if that the tubing is tapered, as I used a pipette. It was the perfect thing. Using a glass pipette was phenomenal for this. And then step 3, you go ahead and get yourself a gas source. You can use argon or helium. You can also use neon. Helium and argon have the best results. And you feed that into the base of the casing at about 0.5 meter a second is what I found was good for my setup. And in the end, you then end up with...
I was always focusing ionized...
Oh, geez,
I was always focusing ionized helium into a point.
I don't know what's going on with my voice there in that clip, but you turn on the power and voila, there's your cold plasma. It's already made that simple. Now, a couple points about why this works. So helium is kind of magical for this purpose, despite its low supply, so to speak. It has extremely high thermal and electrical conductivity. That's super crucial for this working and for making cold plasma. Additionally, the helium is moving, and it's moving past the electrode. These two things combined mean that it takes nothing but a split second to ionize the gas. The gas ionizes instantly, but it takes a little bit of time to heat up the gas on a larger scale. The gas is flowing past. It's highly conductive. The helium has high thermal conductivity, so it dissipates the heat extremely quickly. And also, I mentioned, helium is highly electrically conductive. So as it shoots out the end of the pipette, for example, it acts like an extension of the electrode that's still inside the tube. But now it's cool, it's room temperature, and it's a gas that's ionized, so you can essentially control it to whatever shape you want. And what helps sterilize it is it carries with it ozone, nitrogen oxide, and a lot of electrical current. Life generally does not like those things. And if you were to do it on an open wound, it will sterilize the wound, but of course there is always a mild risk of, okay, those are some carcinogenic things there. Admittedly, an open wound also will have a lot of already lysed and destroyed cells, so you do have a slightly limited risk in those regards compared to doing it to a healthy part of your body. But I wanted to test this. What's the difference between cold plasma and hot plasma on a simple growth setup? This was not particularly scientific. It was more just I wanted to do a basic setup and not have fully conclusive evidence. I swabbed my hands, didn't wash them for a day, and then I inoculated 9 plates, 3 triplicates, a control, a hot plasma, and a cold plasma. I wanted to see the difference. Hot plasma, you can see was doing some damage to that plate there. Cold plasma was hardly touching the plate. I let them grow for a few days, and in the end, hot plasma ended up eradicating life on the surface, as you'd expect. It also damaged the surface significantly, so you wouldn't want to treat somebody with hot plasma. The cold plasma, on the other hand, it's a little hard to see. I didn't get the best growth results. Anybody who knows microbiology is going to, it's not the best growth results, period, anyways. But all 3 plates, I had limited helium, and I just treated the center of each one of the discs. And the center of each one of the discs was identical, where not even the smallest little speck of bacterial growth was present. So I found, non-scientifically, but in a general term, cold plasma was able to eradicate that inoculated area in terms of life, and it did not touch the plate whatsoever. I'm going to skip ahead really fast. Looks like we're a little low on time. I was going to talk a bit about Tesla coils, and all you need to know about Tesla coils, I'm still going to show it, is, Nikola Tesla was brilliant. He wanted to just take the idea of electrical resonance and resonant voltage rise to the extreme. And it's like, what happens if you essentially pile electrical waves on top of each other to a point that they create insanely high voltages? His idea was to create those high voltages, suppress them at the top of the Tesla coil, and then use that for wireless power transmission. So again, I'm going to skip a bunch of slides here. I'm going to go straight to showing the coil that's probably going to burn my hands a little bit. And all you need to know is that you're looking at extremely high frequency, high voltage electricity. Tesla coils are known for a lot of stuff, like sparks, arcs, lightning. They also transmit wireless power. Did not bring the tube for that. I'm going to turn off the mics, and I'm going to signal here in a second to turn it off. I predict this will cause a ton of RF interference on every audio thing, so we're actually going to shut off the audio. I'm just going to do the Tesla coil real fast, and then I'm going to close up here shortly. So please turn off the audio. Thank you. Raise a couple question points in your head, and hopefully you walk away curious.
Jay, this might come back if you want to talk.
Microphone again. Excellent. How to turn it on? Test, test. Ooh, hello. Yeah, so thank you everybody for coming. I'm going to be out gorging myself with food, I think, like the rest of you guys. This is my passion, and this is what I do for my full-time job as well. So thank you very much for being here, and hopefully you walk away curious.